All right, guys. So it's hard to believe we're already in Unit 7, but and what you'll find is a lot of Unit 7 is a lot of review concepts that we've already talked about, and there's not much totally new material. So you'll find that there's a lot of reviews. So this video is just an introduction to 7-2, which is going to be about percent by mass, percent composition, which is a concept we've already talked about. Molecular formulas, and we already know molecular formulas. That's just a chemical formula for a compound, is a molecular formula. And now we're going to differentiate between what we call a molecular formula and an empirical formula. So this is just kind of an intro to that. We had a worksheet that went through basically all the kind of things that you'll need to do in this part of Unit 7. And so all this video is just going over that worksheet. So topics covered: molecular versus empirical formulas, and what percent by mass is. And the main thing is, if given percent by mass, percent composition of a compound, you need to be able to come up with the empirical formula of the compound. Okay, so let's just jump right into it. So this is the worksheet we're going over, intro to 7-2 empirical and molecular formulas. Okay, so we did this in class together, and I just want to go through it and go through the highlights. Okay, so question one, it says benzene is C6H6, and it's asking what the empirical formula of benzene is. So an empirical formula is just the lowest whole number ratio of a formula. So C6H6, 6 to 6 reduces to 1 to 1. So the empirical formula would just be C1H1, or just CH. Okay, so that is the empirical formula of benzene, where this is the molecular formula of benzene. Okay. In question 2, it's just asking for the percent by mass of carbon in benzene. So that's all. Whenever you do percentage of anything, it's just the amount of the part divided by the amount of the whole times 100. And so if it's percent by mass, you want to be thinking like percent by gram. So the amount you want to calculate is not particles, it's not moles, it's grams. So we're going to do the mass of carbon in benzene divided by the mass of benzene times 100. That's how we come up with the percent by mass. So if we look at the molecular formula, we can like assume we have 1 mole of the compound, and so if we have 1 mole of the compound, that means we have the molar mass of the compound. So 78.12, that's the molar mass of C6H6. And then what we can do is just look at the formula, and it says we have 6 carbons, and so we can calculate the molar mass of 6 carbons, and that would be 6 times 12.01. So that's where this number comes from. That is the mass of 6 carbons. So all we have to do is mass of the part divided by the total mass times 100, and we get the percent by mass of carbon in benzene is 92.24%. Okay, and if you wanted to figure out the hydrogen, then because it only has 2 different elements, all you would have to do is subtract this from 100 to get the percentage of hydrogen. Okay. Now, a thing I want you to understand is, if we found the percent carbon in benzene's empirical formula instead, notice we get the same percentage. So CH has a mass of 13.02, and 1 carbon has the mass of 12.01. And what I want you to notice is, if we do the same thing for the percent by mass of carbon in this formula, we get the same percentage. And so that's something to understand. That's something to know. An empirical and molecular formula will have the same percent by mass. Okay? And so that means anything that has this empirical formula, so anything that reduces down to this, would end up having 92.24% carbon. So if you think of another compound that has this empirical formula, C2H2 ethine, C2H2, 2 to 2 would reduce to 1 to 1. C2H2 would have this same percentage carbon, and it would also have the same percentage hydrogen as benzene, as C2H2, as the empirical formula. And that's kind of important to know. All right. So let's make sure we understand what a molecular formula tells us, right? A molecular formula tells us if there's two ways you want to interpret a molecular formula, and these should be subscripts here, okay? If you have one molecule of C6H6, then the subscripts are telling you how many atoms of each element you have in that molecule. So in one molecule of benzene, the molecular formula is telling me I have 6 carbon atoms and I have 6 hydrogen atoms. That's one way to interpret it. But a lot of times in chemistry, we like to scale it up because it's really hard to focus on one molecule because they're so small and we can't see it, right? So instead of one molecule of benzene, we scale it up to a mole of benzene. And the subscripts basically tell us the same thing. So if we had 1 mole of benzene, that means we would have 6 mole of carbon atoms and 6 moles of H atoms, hydrogen atoms, okay? And so the key to this part of the question is I want you to understand that the subscripts in a formula tell you the moles of each element. So if you assume 1 mole of the compound, then the subscripts tell you how many moles of that particular element you have. So in benzene, if I had 1 mole of benzene, I have 6 moles of carbon. And I also have 6 moles of H, hydrogen. Okay? So how can we take that and understand how if we know the percent by mass of a compound, we can find the empirical formula of the compound. So how do we go from percent by mass to empirical formula? Okay. So let's look at number 4. It says the percent composition of a compound is found to be 39.99% carbon, 6.73% hydrogen, and the rest oxygen. So what does that mean? Well, the first thing I want to do is figure out what is the percentage of oxygen. And that's really easy. All we have to do is take the total percentage 100 and subtract the carbon part, subtract the hydrogen part, and we get the oxygen. So we have the full percent composition of the compound. We know what it's made up of 3 elements. We know we got this percentage of carbon by mass, this percentage by hydrogen by mass, and now this percentage oxygen by mass. Okay? So what I want you to understand is we're looking for the subscripts, right? It's asking for a formula. And subscripts equal moles. So the question is, how do I take percent composition, which is percent by mass, and get mole numbers? Because if I get mole numbers, I'm going to get my subscripts. And then once I have my subscripts and I have my ratio, okay, then now I can just do some math to figure out the lowest whole number ratio. How do I get those numbers to be a whole number ratio? Okay. So the first step is assume 100 grams, right? Because this is percent by mass, not percent by mole. So we'll assume 100 grams. And then that means those percentages for those elements are really how many grams of each element you have. So I have that many grams of carbon. I have that many grams of H, not H2. I have that many grams of H. And I have that many grams of O. Okay, not O2, but O. And so grams aren't my subscripts, but moles are. But I know how to go from grams of an element to moles of an element, right? All I have to do is divide by the molar mass. So if we take the percent of the carbon, and now that we said we had 100 grams, now that's grams of carbon, and we divide by the molar mass of carbon, that'll give us how many moles of carbon we have. Okay, we do the same thing with H, but remember, notice that it's just H, not H2, so not 2.02 here, but 1.01. And that's how many moles of hydrogen we have if we had 100 grams of the sample. And then we do the same thing with O, divide by 16, not 32, because it's not O2, it's O, and that we have that many moles of O. Okay, so those are the moles of each thing if we had 100 grams of our compound, and those can be our subscripts, those can be our ratio. So I have C 3.33, I have H 6.66, and I have O 3.33. Okay, now that's not an empirical formula as it is right there, okay, but it is a formula with the right ratio of atoms. And now I just have to get them to be whole number ratios. So the first step, once you get moles of each thing, once you get your each subscript, divide each of the subscripts by the lowest one. And a lot of times, once you do that, you'll end up with all whole numbers and you'll be done. Now, the reason why you want to divide by the lowest one is because that's going to make whatever element has the lowest subscript, when you divide by itself, it ends up being 1. And then you won't be able to reduce it any further. Okay? So understand, this is my formula right now. I just have to get these to be whole numbers. you can multiply or divide by whatever you want. If I do it to this number, as long as I do the same thing to the other numbers, I'm not going to affect the ratio and I'll still be good to go. But to streamline the process, once you convert to moles, right over here, and these are your initial subscripts for your formula, now the next step is to divide by the lowest subscript. Okay, so the lowest subscript is 3.33, and we'll divide we'll divide that 3.33 divided by 3.33, we get C1. Oxygen has the same subscript, so we got O1. And then when we do 6.66 divided by 3.33, we get H2. And now we have all whole numbers, and that is my empirical formula. Now, you don't have to write the ones are understood. So you could say CH2O if you wanted to, but that would be my empirical formula. So from the percent composition, that's my empirical formula. Okay. I'm going to come back to part B here in a second, and just let's review the steps. Okay, so the steps, how do you go from percent by mass to empirical formula? The first step is assume 100 grams. That changes the percent signs to grams. Convert grams to moles of each of the elements. Now those are your subscripts. Divide the subscripts by your lowest one. And a lot of times, like in this example, you'll get whole numbers. But sometimes, every once in a while, you might end up with a fraction. You might end up with like 2.5, or you might end up with 1.33 or something like that. So the very last step is make all of them whole numbers. So what do you think you do when you get a half? You double everything. What do you think you do if you get 0.33? You triple everything. So sometimes you might have to multiply by 3 to make a whole number. You might have to multiply by 2 to make it a whole number. Maybe you get a fourth, maybe you get 0.25, maybe you get 0.75, so you have to multiply by 4. Okay, but that's the last step. But remember, if you do it to one of the numbers, you have to do it to all of the numbers. So like if we go back up to this example, if we divided by the lowest subscript here, but this came out to, instead of 2 for the hydrogen, it came out to be 2.5, then we would double all of the subscripts. If like this came out to be 1.33 instead, then we would triple everything. But not just this number, we would triple all the numbers to maintain the ratio. Okay? All right. So the last part of this lesson is, okay, well, that's the empirical formula, but how do I know what the molecular formula of the compound is? Well, the only way you can do that is if you know what the molar mass of the compound is. So you'd have to figure that out some other way, okay? Or a lot of, especially at this level of chemistry, in the next part of the question, the molar mass of the compound will be given to you, okay? So in this case, they say, hey, by the way, the molar mass of the compound is this, okay? Well, here's the deal. The molar mass of the empirical formula should go in evenly to the molar mass of the molecular formula. And if they came out to be the same number, then the empirical formula is the molecular formula. Sometimes the empirical formula can be the molecular formula, okay? But if we add up the molar mass of the empirical formula up here, we get 30.03. So this is the molar mass of the empirical formula. So if we added up the molar mass and it came out to be 180, then this would be the empirical formula, or the molecular formula. But because it doesn't, we know that this is not the molecular formula. So what do? We take the molar mass of the compound, which they gave us. We divide it by the molar mass of the empirical formula, which we figured out, right? 1 carbon, 2 hydrogens, 1 oxygen. And that should always give us, when we do molecular formula molar mass divided by empirical formula molar mass, that should always give us a whole number. Now, if we round a little bit here, it might end up being, 5.99 or 6.001. You could round at that point. You have to be, you hopefully when you do this step, you get a whole number or very, very close to a whole number. If you get like 6.5, then you probably found the empirical formula incorrectly or something. Okay, so in this case, we get 6. So that's telling you that the molecular formula is 6 times the empirical formula. That's all you have to do. So all you have to do is take your empirical formula, multiply all the subscripts by 6, and now you get your molecular formula. Okay? All right. So that is 7-2. So if you understand all those concepts we just went through right there, you should be good to go for 7-2. Now, again, we'll do official lesson in school, but, a lot of the different things that you have to do for this is just, like mole calculations, understanding ratios and stuff that you already know. So, you know, as long as you understand what we were doing there, you should be in good shape. Okay.